Hello everyone and welcome. In this explainer, we're going to unpack something really cool, literally one of the most elegant and essential mechanics operating quietly behind the scenes of our entire digital world. We're talking about the mechanics of hybrid cryptographic protocols. So, if you've ever wondered how two completely separate networks across the globe manage to establish a perfectly secure line of communication over totally untrusted infrastructure, well, you are absolutely in the right place. Our source material today is incredibly concise, but it outlines the exact mathematical and structural formula used to protect digital information at scale. Let's just dive right in and unravel this together, shall we?
Okay, so real quick, here's our roadmap for today. We'll start with the cryptography puzzle, move into symmetric encryption, then asymmetric encryption, tackle the key distribution problem, and finally wrap up with the hybrid protocol solution.
All right, part 1, the cryptography puzzle.
So our source material presents this puzzle by giving us exactly 4 specific elements that kind of combine to solve a really critical digital challenge. As you can see here, we've got hybrid cryptographic protocols, symmetric key distribution, symmetric encryption, and asymmetric encryption. Now, individually, right, these are established cryptographic concepts, but how our source relates them to one another, that forms the absolute foundation of secure network architectures. Understanding how these pieces interact is absolutely crucial, and it really sets the stage for our entire analysis today.
Moving on to part 2, symmetric encryption explained.
Okay, so symmetric encryption is essentially the first half of the equation presented in our source for securing key distribution. To put this in context, in real-world hybrid systems, think IPsec, symmetric encryption is the actual engine behind the encapsulating security payload, or what we call ESP. Basically, it does the heavy lifting. It provides confidentiality for bulk data payloads, and it does it at incredibly high speeds. Why? Because it uses the exact same key to both encrypt and decrypted data, so it's computationally super efficient. It's basically the perfect tool for seamlessly processing massive amounts of network traffic. But, and this is a big but, this efficiency comes with a pretty distinct limitation when you're trying to operate it entirely on its own over an untrusted network.
Which leads us perfectly into part 3, asymmetric encryption explained.
Right, so this brings us to the necessary counterpart. Asymmetric encryption uses a paired set of 2 mathematically linked keys. You've probably heard of them, the public key and the private key. Now, its primary utility in this protocol actually isn't encrypting bulk data. Nope, it's all about secure identity verification and key transport. Because of the complex mathematical operations involved in generating and validating these key pairs, it is significantly slower. Honestly, it's much more resource-intensive than symmetric algorithms. But that computational cost, it buys us something incredible. It buys us the ability to securely initiate a connection without ever having shared a secret beforehand. A real game changer.
So when we contrast these 2 elements, it reveals exactly why both distinct methods are required by the protocol. Think about it like this. We have the heavy processing overhead of asymmetric math on one side stacked right up against the raw speed of symmetric bulk encryption on the other. Frankly, neither is perfect on its own if you want a complete end-to-end secure communication channel. The symmetric side, fast for sure, but totally vulnerable to interception during the key exchange, while the asymmetric side is highly secure but practically unusable for gigabits of continuous data flow. Basically, they both have a major blind spot.
Now for part 4, the key distribution problem.
Our source specifically zeroes in on the distribution phase as the absolute primary hurdle that needs overcoming here. The dilemma is this: we really want to use our fast, efficient symmetric encryption, right? But how on earth do we get that shared key safely across a wild, untrusted network like the internet? I mean, if you send it in plain text, boom, it's immediately compromised. And this is exactly where protocols like Internet Key Exchange, or iKey, come into play. iKey represents the modern solution to this very problem. It securely negotiates and distributes the symmetric keys we need for our session before any actual payload data is ever transmitted.
And finally, part 5, the hybrid protocol solution.
The text defines this ultimate resolution really clearly as a hybrid cryptographic protocol. But here's the cool part. It doesn't just arbitrarily mash these algorithms together. No, it strategically merges them by combining security associations, or SAs. In practice, what a hybrid protocol does is it establishes one SA for the secure asymmetric control plane, like iKey, to safely negotiate and transport those keys. Then, it links that to a totally separate SA for the fast, symmetric data plane, like ESP, to handle all the actual traffic. It's brilliant. It combines the strengths of both systems to just completely cancel out their individual weaknesses.
Let's just quickly walk through the logic of this 3-step process. Step 1 focuses on our main goal,
we want to utilize our fast symmetric encryption, like ESP, to send our heavy data. Then, step 2 implements the delivery mechanism. We utilize asymmetric encryption, essentially leveraging iKey, to securely negotiate and transport that symmetric key itself. And finally, step 3 is the payoff. Because the asymmetric control plane securely delivered the key across the internet, we successfully achieve safe symmetric key distribution. Once that key is safely shared, the asymmetric job is officially done, and both parties can just communicate at absolute lightning speed using those securely shared symmetric keys.
So to summarize the exact wording of our source, what we've just described is the use of hybrid cryptographic protocols for symmetric key distribution. It's just a perfectly balanced, unified system. The asymmetric protocol safely negotiates the parameters across a dangerous network, which then allows the symmetric protocol to step in and do the heavy lifting of encrypting your actual data payload. This exact principle, this teamwork, is fundamentally what secures enterprise VPNs, site-to-site IPsec tunnels, and honestly the entire backbone of zero-trust network architectures today.
So I want to leave you all with this final thought. Is your symmetric key truly secure before it reaches its destination without a hybrid protocol? Well, the answer, as our source material heavily implies, is a resounding no. Without that asymmetric control plane stepping in to negotiate a secure transport, the symmetric key is completely fragile. It's completely vulnerable in transit. It really requires the precise harmony of both of these systems to create the robust network privacy we all depend on every single day. I really hope this explainer illuminated the elegant logic behind hybrid cryptography for you. Keep analyzing, keep learning, and I'll catch you next time.